Up to this point, we've been looking at a number of different methods for calculating productivity and also the cost of equipment that depend on building up the costs using time and money estimates, but also on assuming that we have some sustained cycle time that is the same throughout a process. And while that might be considered an average, it does not recognize that there are a lot of variables when we look at work and production. All these variables have variations and variance. And if we don't account for those, we're always going to be, I think, significantly different from actual. And in terms of making an estimate, that's not what we want. We want to be able to have a good, reliable, accurate way of determining costs in production. And the only way we can do this really is by considering the variability in all the factors that go into producing work. So, for Chapter 6, as opposed to the deterministic ways that we've been using up to this point, we're going to talk about stochastic methods for estimating productivity. And in particular, we're going to look at some simple probability and statistics that help us to make better estimates of productivity and costs. And also, they're methods that allow us to take a step up and actually model different costs and activities. So, in developing mathematical models, and that's exactly what we're going to be talking about, and hopefully we might be able to spend a little more time later on talking about this too, we need to talk a little bit about probability theory. And again, we're not going to go too far into it, other than to say that, there are certain components of costs that do vary, and that we want to be able to estimate how they vary, and we're going to do this by measuring items in the field or analyzing records of work. And based upon those measurements, we're going to develop frequency distributions that replicate the distribution of these measured items. And then we're going to use these frequency distributions to actually do some calculations. I think we want to start out, I think, first by considering an example. And example 5.3 is a good place for us right now, but say we have a haul length of 1,300 feet and a loading time of 3 minutes, a variable time of 4 minutes. Remember that variable time comes up with all those miscellaneous items that affect work and that waste time away. So what we want to do is compute the sustained cycle time and the optimum number of hauling units N for that sustained production rate. This is the work we were doing back in Chapter 5. And if we have a hauler with a capacity of 20 bank cubic yards and a shift is 8 hours long and waste time is 2 minutes per cycle, we're able to go through using the methods that we've been looking at in Chapter 5 and in Table 5.1, and we can figure out the fixed time. And F then is 4 plus L equals 7 minutes. And then again, if we apply that to equation 5.12a, then we can take that waste time out of the fixed time and we get 5 minutes. And we're able to then calculate a total cycle time of 5 plus 4 plus 3 equals 12 minutes. Now, one of the things that we do as we calculate this number, we're able to know that out in the real world, that 12 minutes does vary. And if we were to actually measure those Hall true cycle times, we might end up with a distribution like this. And down on the horizontal axis, there is that cycle time m, the number we just calculated. And then on the vertical axis, we have number of observations, how many times we saw that particular time. So if you were to stand out on a job and watch trucks get loaded by a loader, you would find that there were about one time when you saw that it took about 10, just a little over 10 minutes for the cycle to happen. And there might have been one time when it took about 20 or 21 minutes for the cycle to happen. The most times that you'd measure, you would have seen that you would have had about 20 or 21 times when you saw a cycle somewhere around 14 minutes. And again, trying to find an even one, about 17.5 minutes is this frequency, and you would have measured that 10 different times. They wouldn't have all come together. You would have seen one that was 10 minutes, and then maybe one that was 19 minutes, another one that was 14 minutes, and maybe another one that was 15, and then another 14. And as you counted over the day, you would end up with this kind of distribution. This is as opposed to that deterministic number that we came up with, that again is fixed and doesn't really account for the fact that a lot of things happen that cause work times to vary. If we again go back to this particular now frequency distribution of Halls, one of the things that we want to be able to do is write an equation so that we can use it in a calculation to make an estimate. And to do that, we're going to try to estimate a standard type of probability frequency distribution. And in this case, just by looking at the distribution, you see that it starts at 0 or close to 0, peaks, and goes down. And it looks a lot like a triangle. So that gives us a clue. Now there are programs that will fit distributions of observations like we have here and fit them to different probability curves. And if you go out on the web, you can find there's several nice free ones that you can get and put distributions in, and then they will give you a probability frequency distribution, and it'll fit the parameters for this curve. In general, though, what we're going to be doing is that we know that A is the lowest probability value. That was the one at the beginning we saw back at 10. B is the highest possible value. Here was at 14. C is the most likely value, or here B is the highest value, I'm sorry, at 20. C is the most likely value. And then this point is given by the equation 2b minus a, which is the most likely value. So again, there are equations to do this, and we're not going to test you or pretend to turn you into distribution fitting experts, but I think what you need to know is you're going to be looking at your data that you collect in the field and seeing what type of distribution it has. You all know a normal distribution. You've all seen that curve for many, many years. And again, this triangular distribution is just another shape that you can have. There are a lot of different shapes. We'll talk about a couple more as we go on. As I mentioned, there are different ones, and there are 4 most common distributions. So if you generally stick to these distributions, one of the things that you'll find is that you'll get familiar with them, and you also find that they work pretty well when it comes to simulation modeling. We just saw the triangular distribution, and You use this when you can only estimate the lowest possible value and the highest value and the most likely value, triangular, 3 points. You can use a Poisson distribution, and that's in figure 6.3, and I think we have that one right here, a Poisson distribution. This is commonly used in simulation work, and in a Poisson distribution, it's appropriate when variation in the values are random. And we often use these for queuing problems, in particular for public traffic, traffic flow up the traffic signals, or arrival of customers into bank queuing lines, or at a checkout line at a grocery store. And in order to use this distribution, you have to have 4 conditions. First one is that events can happen at any of a large number of places within the unit of measurement. In other words, they jump around like I was mentioning a couple minutes ago. There's a low one and a high one, and they don't fall sequentially or in any particular pattern. They happen within that continuum. At any particular specific point, the probability of an event is small. Events happen independently of other events, that's what we were just mentioning. And the average number of events over a unit of measure is constant. So you keep having the same, if you have 100 events every day, you'll have 110 the next day, and 90, and then 100. You have a range. And there are rules, again, for that type of checking. We're not going to go into that. I'll refer you to a couple videos that you can get a little more information on. Our normal distribution, and we can go up to 6.4. You can see the normal distribution that we're all familiar with. And this is the bell curve, and it's used when a value is subject to many different sources of uncertainty or an error. And it has specific qualities, again, that you can look at. First of all, the density function is symmetric about its mean value, right? You see that right here. The mean value is here. The rest of the values are split on each side. Same thing. What varies? Again, there are factors that will, the skew and the kurtosis in particular, will give you, and the variation, the variance, the standard deviation will shape these curves for you, but they're all normal probability frequency distributions, normal curves. What else? The mean is also its mode and its median, and that's not necessarily the case with these other situations. And what else? 68.27% of the area under the curve is within 1 standard deviation of the mean, right? Kind of a standard number you've learned. On each side of the mean, 1 deviation, you have 68% of the curve, and within 2 standard deviations, 95.45%, and 3 standard deviations, 99.73%. So you're able to use the standard deviation to estimate how great the probability is and to hone in on the accuracy and the reliability. There's one last distribution that's commonly used. Again, there are a lot of different distributions, but the uniform distribution, and we'll go up to 6.5, the uniform distribution is just what it said. A is the lowest possible value, B is the highest possible value. The distribution is the same anywhere in between there. The frequency of occurrence is the same all along there, and that value is 1, B minus A. This is used when there's a high value and a low value, and the chance of observing any value whose range is equal to or all the other values is uniform, is the same. Okay. Now, we'll flick through, and again, one of the things you notice, you'll see here on the Poisson, again, different shapes, but the important thing is what's happening is lambda is changing, and a factor, the variation is standard deviation is changing, but they're all the same. Different types of activities are going to have different shapes of a Poisson or this random arrival curve. Same thing with the normal distribution. Different activities. You may have 3 different activities. The loader, the truck, you might have a bulldozer at the other end doing work. They could all be represented by a curve with a normal probability frequency distribution. They just have different factors that make the curves differently for you. And again, this uniform distribution. So if we're going to jump from a deterministic equipment model to a stochastic model, there's several things you have to know and do. First of all, you need to know and get together all the variables that are going to be part of the model. Then you develop a mathematical relationship for each variable. You identify the possible ranges in value for each variable. You associate a probability frequency distribution with each variable that you're going to vary in an impending simulation. And then you're going to develop a remaining input that's required by the simulation software that will be used. And again, you're going to use some type of specialized program. And you can buy simulation programs. But also you can make a simulation easily in a spreadsheet. An Excel spreadsheet will allow you to do that. And I will give you some information about some spreadsheets that you can play around with and do as we go on. But you don't need expensive software, although you can go out and buy $5,000 or $10,000 pieces of software to do simulations. And what they really do between that and a spreadsheet is, first of all, in a spreadsheet, you do have to write your code up originally and put things together. And whenever you want to make variations, you're going to be recoding or changing cell values. A simulation software just allows you to build up models easier. And by models, I mean the chain of events, say from a loader picking up a bucket full of material, turning around, going over to a truck, dumping it into the truck, returning back to the pile, and at the same time the truck pulling away, driving to a dump site, dumping the site, and then returning. That's a chain of events, and that chain of events just continues on. And that's what the simulation software would allow you to generally create blocks of code, and each block would represent, for example, one would represent the loader, one would represent the truck, or it could be broken down finer. You'd have one that represented the bucket filling, one the travel to the truck by the loader, one the loader dumping, one the loader returning. The simulation software allows you to break that and to be able to go as fine or in depth as you want. And again, you see if you can start at a macro level. A block is a loader or a block is a truck, or you can work down to a micro level, and each of those levels are going to have probability density functions that you're going to fit to that data, and that you can vary in order to make the model more or less accurate, or more accurate for you, more detailed. Now, in order to create these statistical models and probability models, you have to do some analysis. It's common to use average times or loads, and back in the deterministic methods, back in chapter 4 and 5, we were assuming average times or loads. And just to be clear about what we're talking about, because you already used a couple of these other terms tonight, average is a statistical measure, more properly called the mean. And along with the mean come a median, which is a middle value of your data that you've collected, mode, which is the most frequent value in the distribution, and then some type of measure of central tendency, which describes the axis around which the data is oriented. And by measure of central tendency, we mean a standard deviation or variance. So you're used to calculating means and standard deviations. Those are the factors that determine or describe the shape of a curve, and those are the kinds of numbers that you need to be able to collect in order to make a successful model or an accurate model. And I started talking about variation already, and if we go back again, look at figure 6.1, you see the variation of cycle times for that hypothetical haul crew. And in the case of that distribution, you can go back and look at it, and you can see that that's most likely the case just by observation. The mean was 14.9 minutes, but the values range from 10 to 20 minutes. Okay, we already saw that. The standard deviation of the data is 2 minutes. That's calculated using the standard statistical formula. And again, you can do it in a spreadsheet. If you go into the function blocks, you can determine the mean and the standard deviation value for a set of numbers using the functions in Excel easily. If we assume that the cycle time was normally distributed, then we'd find that 68.27% probability that any actual cycle time would be somewhere between 12.9 and 16.9, and you get those numbers by subtracting one standard deviation or adding one standard deviation to that mean. Okay, mean is 14.9, standard deviation is 2, so you get 12.9 or 16.9. So roughly 2/3 of the time the haul crew will be achieved, or that's at 68.27% number, will be achieved actually with actual cycle times that are within 2 minutes of the mean. In other words, 68% of the time that haul crew is going to be having cycle times of between 12.9 and 16.9 minutes. And if you think about it, this is really a lot more natural. You aren't going to have those cycle times every time being 12.9 minutes. 12.9 minutes. They're going to vary. And if you know, though, that there is a range, and again, the 68.27% gives you a probability of occurrence, you now can associate that with data, input data or projected data or even historic data, and you can use that in a simulation or a stochastic model. Now, one thing you may notice is back at the beginning when we first talked about figure 6.1, we were looking at fitting a triangular probability distribution function to the data. And a minute ago we were just talking about fitting a normal distribution. Which one do you pick? Well, again, there are programs, as I mentioned, that will help you fit a set of data to a probability function. But a lot of it has to do with accuracy, or even better, a lot of it has to do with your ability to be able to run a lot of different models to see the difference in the numbers that come out and compare them. and then use good judgment to make a final decision. The nice thing about simulation, and the reason that I have been doing simulation for so many years, I've been doing many, many years, probably 40 years, is that using a computer in a simulation model, whether I wrote it myself or used a program, is I could do many, many simulations of a piece of work. And the simulation is that it would run a computer imitation of that work, an imitation made up of equations and probability functions. And I could run simulations using the triangular function, or I could run simulations using the normal function and see which gave me the most reasonable numbers, or numbers, again, using other statistical parameters, which gave me the most security that that number would be a good estimate to use for my final answer. So you can use both. You can use others to fit. There really isn't a rule to say which is right or not, but there are a couple measures that you can use in your head so that you can stay in the terms of doing things that are reasonable. For example, if the standard deviation is relatively small as compared to the mean, then it indicates the variation will be correspondingly small. So also what that leads you to is that you can use the mean as a predicted value for the parameter with good confidence, but also that your number is going to, stay very tight. The different simulation values, the outcomes are going to be fairly close together. Generally, for a normal distribution, we say that there is a normal distribution if the standard deviation is about 25% of the mean or less. Okay. If the mean or the standard deviation is greater than 25%, then you're going to be using some other type of density function to better represent the wider range of values that might be reasonable. In other words, if the standard deviation is relatively large as compared to the mean, then it indicates the variation of the particular parameter you're estimating with it's going to be great. And you'll need to use a value that is greater than the mean as a predicted value for that parameter in order for you to have more confidence in the final number. You see, that's what we're really looking for. Literally, you're looking for confidence and how secure you are in the output of your model when you're all done. Again, another example, if you look at, we go back to that figure 6.1 data, and we use a triangular distribution to fit it to it, then you can see that we can make a fairly good estimate. Now, it tells you that mean isn't right in the middle. In this case, it's a little on the low end. You may want to use or know that you have to increase the values that you want in order to be accurate, or to run more simulations or test the sensitivity of your model. And testing the sensitivity means simply that you run the model over and over again. You change one variable, leave everything else the same, and you see how much the answer changes. And by that process, you can find which variables have the greatest impact, and also which distributions therefore have the greatest impact on your final numbers. Again, you can fit that triangular distribution to that set of data. Remember, you gained these pieces of data by taking a stopwatch or video camera and watching activities, a loader truck crew working, and measuring how long it took for them to do each cycle, and then building a chart up. There are important types of data that we collect when we're looking at building a model, and this is pretty much the same for any type of production model that we're going to be working at. You need cost performance data, because that's one of the outcomes, that's one of the things the numbers we're looking for in the end is cost to do work. We want production performance data. We want to know how many units of work and how quickly they can be done. We need data on maintenance failures, and we want that type of data so that we can predict, again, how equipment will operate and account for that in the performance curves or the probability distribution curves for the equipment. And then we want labor performance data. How do people work? Just like the machines and just like all the other activities. Labor is going to, people are not going to act, they're not going to be machines. They're going to perform at different rates during the day, during the week, over the course of the year, depending on what the weather is, how they feel. A whole bunch of situations that vary how labor performance changes. Again, if we're looking at cost performance data, we want to know about actual costs of doing work, measured amounts of work. And then we're going to try to relate those actual costs to estimated costs in the future. And we can express this as a ratio to help us determine how accurate we are. For example, if we have an actual cost, we're going to divide it by the estimated cost. It gives us a cost performance factor. Ideally, that factor would be 1. In other words, the actual cost would be the same as the estimated cost. If the ratio is greater than 1, you need to investigate to find out what was different and adjust those factors for future projects. Okay, this is a way of testing your model and being able to make it more and more accurate. It's a form of calibration, although I don't like to say we calibrate our models, but this is a way that tells you that you need to look at your probability distributions, if they're the correct ones, if they have the right components in them. If the ratio is less than 1, it means that the estimate was too conservative and you bid too high. And if you bid too high, you don't win a project. So you can't have a ratio too much less than 1. Again, what are you going to do if it's less than 1? You'll go back to your distributions and you're going to adjust them so that they change your final estimated numbers and try to bring them back closer to 1. If you have a range of, say, 0.95 to 1.5, that probably is as close as you can get, and you should have reasonable numbers. Again, it doesn't mean you can't try to estimate, but just remember the estimation, by its nature, simulation, which is what we're doing, means that you're going to run a particular problem and set of equations 100 times or 1,000 times. Every time you'll be starting with a different seed value, and each answer is going to be slightly different, and you're going to take those 100 or those 1,000 runs and you're going to average them, and that'll give you the actual cost for the given item. So as each of those values is going to be different, and every time you run the model it's going to be different. And so you want to be able to know that you can go on, but if you can get between 0.95 and 1.05, that's probably more than accurate enough for taking care of business. Some of the things that also affect that cost performance ratio is the kind of data you're including in the numbers that you're comparing. In other words, if you're using cost data, one of your output numbers is cost data. Remember, over time, costs change because of inflation. And if you don't somehow go to a constant value, your numbers, because of inflation, your actual costs will increase over time. And if you don't account for that inflation, you get an unrealistic projection in the future based upon the past, which may not be accurate. Also, age of data that you use in the calculations can affect the answers. Simply that over time, again, equipment changes, processes change, values due to other reasons besides inflation change, and if you use old data, again, it might not reflect the future, and it'll make your ratio be out of whack. And that's, again, you have to make sure that you adjust, in the best case, adjust for inflation or bring everything to a constant value. And you want to use data that's fairly new. You might, and if you use a system to collect your data, that can peel off the last 3 years or 5 years, depending on what the stock market is telling you and what the engineering news record, construction cost factors are doing, then you're going to have a lot better number. And that's one place where you can look at inflation and see how data is being changed over years. You use the cost of living index, but more accurately, you'd use something like the engineering news record cost of construction index, and that would give you a good idea of what's happening in terms of inflation. Again, one of the things you want to know about and check is production performance. Just like we checked the cost performance a minute ago, you can check production performance by making a ratio of actual to the estimated, and the estimate actual is what you would have measured in the past. Estimated is what you're going to calculate it using a model that you built. Again, you're going to want to make sure that that ratio is fairly close to 1. One of the things that affects production factors is if you estimate that all the machinery will be able or be available all the time during a project, and this isn't a good assumption. And one of the nice things about modeling, even though it's based in probability functions and computer model techniques, is that it does represent or replicate real-life conditions. And if you go into a model and you are assuming all the machinery will be available all the time, that certainly isn't a proper assumption. It isn't a good assumption in terms of real-life situations. And if you don't have aggressive preventive maintenance and repair programs to maximize its availability, you won't have confidence that this could be the case. So that's, again, one of the reasons why you have to collect maintenance failure data. Remember, that was one of the items that we listed a couple minutes ago. You need to know how well data is taken care of, and you need to do it for all the machines on a project that you'll be using in your organization. Remember, there are lots of pieces of equipment, and we've been looking at that are used on a construction project, and the failure of any one of those pieces will at a minimum cause a delay. It might be just a short delay, but again, that goes into that wasted time we've been talking about. But you also can have major failures where the delay will be extreme, and where it can cost the profit on a project, or result in a penalty because you have to pay liquidated damages when you can't meet schedule, a mile point, or an end date. So that a machine going bad can be an expensive proposition. So you want to collect data on how well it's maintained so that you can calculate how available a piece of equipment is. For example, here's an example. If we have a bulldozer that we normally use for 5-10-hour shifts a week, and we do it for 50 weeks each year, okay, everybody takes 2 weeks of vacation. In the past 3 years, if it's been available because of breakdowns or maintenance and servicing, in the first year it was unavailable 44 hours, in the second year 150 hours, in the third year 163 hours. And if you have an earth moving crew who's going to need to have a sustained production rate of 2,000 cubic yards per day, this assumes 100% availability of your bulldozer. What is the estimated production rate for a project that will last for 1 year based on the data that we know is the case? In other words, that machine hasn't been available 100% of the time. In fact, if you look at the numbers, 44 hours the first year, 150 hours, and then 163 hours, it actually, as it gets older, is available less and less time. Again, this might be a symptom of poor maintenance or hard conditions that it's working in, poor operators. One of the things you're going to want to deal with, besides solving the immediate problem of what is a production rate, but you're also going to want to investigate why is the amount of breakdown time, unavailable time, increasing significantly on and on. So that's a different problem, but that's one of the things. If you want to look at how do you maximize production, you maximize availability of equipment, and there are a lot of reasons why equipment isn't available. But getting back to this problem, if we see, we can go ahead and calculate the maximum availability, which is 10 hours a day, 5 days a week, 50 weeks a year, which is 2,500 hours. And then if we find that the average yearly downtime goes up to the 44, the 150, and 163, so we add those together, divide by 3, it's 119 hours per year. And then we can have and calculate an adjusted production rate. And here's that 119. So 119 divided by 2,500, the total number, gives you the amount, the percent unavailable, doesn't it? And you subtract that from 1 or 100%, that gives you the amount of availability. And then if you multiply that amount of percent of availability by 2,000 cubic yards per day, it tells you that you have, based upon this historic average, 1,905 cubic yards per day is the production rate for that piece of equipment. So you can see that by reducing these numbers, you can increase the availability because this number will go down, and you can increase productivity. So that's part of the process. Now, we also know, again, we're using the average, is that in a simulation model we could set this up also with the mean, which is 119, and the standard deviation calculated from these three numbers using the traditional standard deviation calculation. And you could actually run a simulation that would give you another estimate, and it's probably going to be somewhere close into this particular number. And as I was just talking about, you're going to do that by using a Monte Carlo simulation theory, which means that you take a random number generator and you feed the probability distribution. And if we go back again, we can create a probability distribution for equipment availability using the information we have here. 3 years of data gives us a mean, a standard deviation. If we assume a normal distribution, we're able to go in then using Monte Carlo techniques, a random number generator and a spreadsheet, and go ahead and calculate these adjusted production rates. That's exactly what Monte Carlo means. So if we were to look at an example, if we go back to example 5.3 and that we've looked at, if we have a 1.5 cubic yard front end loader and we're going to load dump trucks with a capacity of 9 yards, it's a small little dump truck, and the loader takes 0.4 minutes to fill and load one bucket, and the travel time to haul is 4 minutes. The dump and delay time are 2.5 minutes. Altogether, we find that L equals 2.4 minutes. C equals 8.9 minutes, right? Loading time. Our cycle time is 8.9 minutes. Okay, so then we're going to have able to calculate N, which is 3.71 haul units. So what are we interested in? Because we have 3.71, we aren't going to have 3.71 units. We're either going to have 3 units or 4 units. And if we have 3 units, we see that we can have 182 cubic yards per hour hauled. And if we have 4 units, we can have 225 cubic yards per hour, which is in actuality the loader productivity. So by having an extra truck, even though there's extra costs, we can maximize the loader productivity. If we only use 3, we have times when that loader is sitting. We talked about that already, so this is just a verification of that. But using our stochastic methods, again, that means that we went out and we watched the work being done and we timed it, and we found that actually 3 of the variables had ranges of actual times rather than a specific one value. For example, first, the time taken for the loader to load a single bucket actually varied between 0.3 and 0.5 minutes, where 0.4 is the most likely time, the mean. And because the haul was over a public road, remember we talked about this, that you'd have to change your truck's travel time because of public traffic. For example, it would be 3.5 minutes if there was no interference, no public road traffic. 5 minutes if the truck got stuck behind a slow-moving vehicle. And the average time observed actually turned out to be 4 minutes. And finally, we find that the delay time was a function of the truck's ability to pass through a traffic light and make left turn across traffic. Okay? And that means it would vary between 1.5 and 3 minutes. Okay, with each 0.5 minute increment as likely as the other, because basically we had a random situation. Okay, and that's really what you mean when you have a large variation, that you have a random situation. But again, you see, what we're assuming here and what we've taken a step on is that the real life situation isn't a constant. It isn't factored by constants, but there's a lot of variation. So then if we use, again, the same deterministic equations we looked at in example 5.3, we could develop a spreadsheet. And we use @RISK. And @RISK is a software add-on for Excel. If you go into your computer and Google @RISK, you can go to the @RISK site and you can download a 15-day trial. And if you are interested in modeling, go ahead and download the software. Again, you could, At-Risk just provides you built-in functions, and that's really what it does. It's an expansion of the Excel functions. You can do all the same things by writing formulas into a spreadsheet cells, but it just takes time to do that. But in this case, the author's gone ahead and used At-Risk to do some simulation, and what they found is that for the load time, they assigned a triangular distribution with 0.3 minutes as the lowest value, 0.5 as the highest, so 0.4 is the most likely. And this is just a designation of what that triangular distribution looks like. And they did the same thing with the truck travel time. We had a triangular distribution, 3.5 minutes to 5 minutes, and 4 minutes as the most likely value. And again, that's the description here. And if you plot those out, you see that you get 3 different distributions: the loader time distribution, the travel time distribution. Remember that delay and dump time, if you couldn't tell by the definition of the words, it was a uniform distribution that we had out there. So for this particular load and dump situation, we can describe what's going on using 2 triangular probability distributions, one for the loader, one for travel time, and a uniform distribution for delay and dump time. Again, I'm not going to turn you into modelers, but you can see that if you use different values along these curves, along these distributions, the curve that describe these distributions, and keep plugging in different values, you're going to get different answers. And again, what you do is you would run a simulation 100 times or 500 times, and the number that you run is always dependent on the amount of time you had for computing, how long it took for a particular simulation model to run. The bigger, more powerful your computer, the more times you can run it quickly. But then you take all those answers, the output, all those runs, and you average them up, and that gives you your final answer. So what do you do? Let's say you've gone ahead and used At-Risk and you've run a bunch of simulations, and what do you get? In this case, if we run 100 iterations, and that's what each run of the simulation is called, an iteration. And this shows you what kind of values you get. This is your simulation output, and output 1, where you use n rounded up to 4. If we went back to chapter 5, we'd get a value of 225. But if we, in our simulation, we'll find we have minimum value of 180, a maximum value of 288, and a mean of 227. And we also can find a 5th percentile and a 95th percentile, a wider range of the values of our production. Okay. And if we did a simulation where we're using 3 trucks, again, you'd see what we would calculate first, and then with the minimum, the mean, the maximum, and again, a bigger picture of the range. If we plotted out those values, we'd see that, again, because the input comes from different values and probability functions, we would get a range of answers. And those are the ranges that were in that previous table. A 3-truck crew and a 4-truck crew. And what do you see? First of all, the means are different, right? More production with 4-truck crew, less with the 3-truck crew, but these ranges overlap each other. So there are times when a 4-truck crew will only get 180 yards of production, and also that'd be the same case for the 3-truck crew. And there are times when that 3-truck crew would produce as much as a 4-truck crew. Again, this is if you think about it on the face of it, this is a very realistic situation. Things vary over a workday and over a project's life. And what you see ultimately is over the long term, that 4-truck crew is going to have greater productivity just because there are 4 trucks there. But it isn't a hard and fast case where you'd see that 4-truck crew is always most productive. And this is one of those situations you'll find out in the field where somebody will come by and notice when that 3-truck crew is being especially efficient and say, well, you only need 3-truck crews, but not realizing that in the long run, the long term, that 4-truck crew really will give you more production. But the important thing to note is that by doing these simulations, you see where this overlap is. You see what the distribution of the production values is, and you're able to make a lot better guesstimate or estimate of what's going to be happening in determining production values or cost values for a project you're going to do. So what you can also do is start looking, because you have this nice number now, this nice information, that you can play what ifs. You know, you can say, what if crew needs to have a minimum hourly production rate of at least 225 cubic yards per hour? If we go back, you see that both the 3 and the 4 truck situation are able to meet that particular amount of production, right? It's within the range of both of those curves or distributions. And we can go and then look at the figures. Again, this is figure 6.8, and you can go in here and look at these probabilities. That's what these are here. These are probabilities of a particular value happening. And we can see that there's a 15% probability that 3 trucks will produce at least 225 cubic yards an hour. Let's go and look at 225 right in this area, and you'll see that you're going to have right around in this area about 15%. If you look at the 4 truck, and here's that. If you look at the 4 truck situation, you'll see that for that 225 production, again, you've got around 15% where that curve's going to be coming down through here. Remember, the curve you're going to be using isn't the steps, it's a curve that's going to be fit along the data bars like this. All right. So what we'll see and what we'll find is that the 4 truck crew is going to have a probability of 50% of meeting or exceeding this target. And the 3 truck crew is only going to have a 15% probability that it'll produce at least 225 cubic yards per hour. So this allows you to quantify risk. And you can say, I want to use 3 trucks, but you know I've only got a 15% probability that this is going to work out for me, that I'm going to have a sustained production of 225 cubic yards per hour. But if I use the 4 trucks, and that'll maximize my loader capacity, I've got a 50% probability of meeting or exceeding my target, which is 3 times the other probabilities. So I'm probably going to go with the 4 truck scenario and say I've got a better chance of meeting my goals. Now, kind of built into what we've been talking about is the fact that what we're really measuring is service times of equipment, queuing times, in other words, how long they sit in lines waiting to be serviced, that those dump trucks are going to be waiting for the loader to service them. The heart of simulation and the heart of production work that we're talking about here is queuing theory. And there are three basic components to queuing theory. First, the arrival of customers, and those customers can be haul units or trucks or scrapers or people walking up to the counter in McDonald's waiting to be served or to order. The queue discipline. The queue discipline simply means do you have one loader, or do you have two loaders or three loaders? How do the trucks in line for those loaders line up and wait to be serviced? It's the same thing when you go into McDonald's. If there's one person at the counter, it's a single server. If there are two, there's a multi-server or two servers. And you go on and on. You ever get frustrated when you go into the bank or McDonald's and there's no line set up, so everybody's kind of massed around, and when somebody comes up to serve the customers, nobody knows where to go, or there's no order, and someone who just walked in is just as likely to be served first as someone who's been standing in line for 10 minutes. And that's what we're talking about with queue discipline. Finally, you have the service of the customers, and that's the productivity of the loading facility. How long does it take to actually serve the people that are coming? Does it take 30 seconds or 10 seconds for the bucket to be emptied? How long does it take for you to get taken care of by that server you've been waiting for? When we're talking about queuing theory, we have two important formula that we want to know about. One is the mean waiting time. How long does that truck stand in line waiting to be serviced after it arrives in line? WQ. And that's a function of lambda, which is the mean arrival rate. In other words, the number of trucks per unit time, trucks per minute, trucks per hour, trucks per minute usually. And mu, down here, mu is the mean service rate. That is, how many haul units, trucks per hour can be serviced. That makes sense, right? Waiting time depends on how quickly trucks arrive as compared to how quickly trucks can be served. And ideally you want the service rate to be greater than the arrival rate, otherwise W gets larger and larger and your queue gets longer and longer. You also want to know about P, the probability that the facility is idle. In other words, this tells you lambda divided by mu taken away from 1, it gives you percent, and it tells you how long, or the probability that your loader will be sitting idle. You certainly don't want this number to be large, so again you want to make sure and have just either the service time or the arrival rates to keep P to a minimum. For example, in 6.3, if you have a ready-mix concrete company, right, and you're going to replace your fleet of mixer trucks, and you want to have or determine the optimum number of trucks. And what again is going to be make it optimal? You're going to have the number of trucks and how quickly they can arrive at that plant as compared to the service rate of the batch plant, how quickly the plant can fill up a truck with concrete so that it can go away. So you can have a lot of other steps, but this is a basic one. How many trucks? How quickly can the batch plant load the trucks? And if you have mixer trucks with a maximum capacity of 12 cubic yards, and orders are on a first come, first served basis, and that's part of your queue plan, or how the queue is set up. Service aisles are set up. You've got one server in this case, and the trucks arrive on a random basis. And again, that means you can use that a specific type of probability distribution function that replicates random arrivals. And there's some other information. Some orders are placed in advance or scheduled, but those don't affect your overall rate because they're spread out during the day. So you can really assume that all your arrivals are random, and in that case you can use your Poisson distribution. That's what the Poisson distribution assumes. Random arrivals, particularly it's used for traffic, whether it be trucks going to a batch plant or people arriving at McDonald's to buy hamburgers. So on an average day, the company will fill orders totaling about 480 cubic yards of concrete with an average load of 9 cubic yards, and the batch plant can discharge concrete into the mixer at a rate of 2 cubic yards per minute, and the total ownership and operating cost of the plant, including labor and overhead, is $1,500 an hour. Okay, we need again go back to an earlier chapter about that ownership and operating cost. Batch plant is just another piece of equipment. You have the same cost for the trucks, ownership and operating, and it's $80 an hour. And again, you can have a single channel queue. N equals 1. The batch plant is the loading facility. So what do you do? And again, that seems like a lot, but you really find that the arrival rate, lambda, you can calculate that. You got 400 cubic yards a day, and you've got 9 cubic yard loads for 8 hours a day. And so you can have 6.67 loads per hour, or 53.33 loads a day. Okay. And so you can have also a service rate, mu. It's 2 cubic yards per minute. If there's 60 minutes in an hour, and you know that you can have 9 cubic yards per load, you're going to have 13.3 loads per hour. Okay. Arrival rate, 53.33 loads per day. Service rate is 13.3 loads per hour. And from equation 3, then we can go ahead and calculate average waiting time. It's 4.8 minutes per load. And we can calculate the probability of delay, which is 0.5, just by substituting. And then we can go ahead and calculate the average total daily waiting time for the fleet, which comes out to be 4.26 hours per day. And the average daily loading facility idle time, 4 hours a day. So you see that plant is going to be sitting idle half a day. And you can look at the optimum number of trucks. The cost of waiting trucks equals the cost of facility idle time. Alright, so if we know the cost of waiting trucks is 4.26 hours per day, then you're going to multiply it times 80 times n, and the cost of the idle facility is 4 hours per day times the cost of facility, and there's one plant. Then you're able to set those equations equal to each other and solve for n, and it tells you that the optimum number of trucks is 17. So in this case, you have to make a rounding decision. If you round up to 18, each truck will load an average of 3 loads per day. And again, you could round it down and do another calculation, and so it's easy to see that queuing theory can go to help you make a basic decision about even the number of trucks based upon costs and efficiencies. That really, because it accounts for variation and the fact that nothing is uniform over a day, that you can have some reliability in. Again, when you do some simulation, depending on the program, whether it's a spreadsheet or some type of off-the-shelf program, the output's going to be specific to the program used. So again, a lot of times the decision on what software to use depends upon how much information you have and how it's laid out and how you can make reports. But regardless of that, you as the person estimating or using the data, what you need to do is have a clearly written set of decision criteria that you can use to measure whether data tells you there's a success or a failure for each alternative. And it may be minimum waiting times of haul units or maximum daily production rate or minimize unit costs. But before you get into the analysis, you want to be able to define what your target is so that you know what to compare and make a determination of if the situation you've modeled makes sense, and also if it's a successful simulation or not, or it's being accurate for you. If you're going to use that output to do cost estimating, you have to do several things. You have to select the crew size and the competition. You have to select the production rate that flows from the crew size and the composition, right? You have to gather ownership and operating cost data, just like we did in the example a minute ago with the concrete plant. You have to apply those costs to the crew's production rate and machinery and facilities. And then you can go ahead and develop unit costs for each item of work that the crew will accomplish. Okay, so you're going to do a simulation, and then you're going to go back to the deterministic process we've been looking at earlier, and you can combine them to come up with unit costs. For example, if you want to calculate the unit costs for a crew given the costs of the 4-truck haul crew, if you have a loader with an operator, it's $77.45 an hour. And you have a truck with an operator, it's $83.75 an hour, which is probably a little high. You have an hourly crew cost then of $77.45 plus 4 times $83.75. Remember, you had 4 truck all crew right here. So that tells you you've got $412.45 an hour is the hourly crew cost. And then again, if you go back to the output that we saw earlier from our simulation, where we had 227 cubic yards per hour as the expected production, then you can calculate cost per cubic yard, which is 412 divided by 227, or $1.82 per cubic yard. Now, remember that this only includes a direct cost of labor and equipment, and you have to add markup for indirect and overhead and profit. Now usually that's not your job to add that markup, and as an estimator you provide the basics, and then someone else usually applies those factors. Remember, here's table 6.1 and here's that 2.27 again that we looked at. You know, we can use this information for a lot of things. We can look at production management. Say we have that project with a 4-truck haul crew, and they're going to work on a total of 175,000 cubic yards of aggregate that you need to haul by that crew. And the crew is going to work standard 4-hour work week. And what we need to do is calculate the daily and weekly minimum production rate based on the expected production rate from the simulation. And the bottom line is you want to know how many weeks a project should last. So if you've got an expected daily production of 227 cubic yards per day, remember that's what we simulated, or altogether it's 8-hour day and 4 trucks, right? 1,816 cubic yards per day, and that gives you 9,000 cubic yards a week, right? And the expected project duration then is 175,000 cubic yards divided by 9,080 cubic yards per week, or 19.3 weeks. Obviously you could also calculate how many days, can't you? If you know that you've got a 5-day work week or whatever, 6-day, then you'll get a different answer. But in this case, 19.3 weeks is how long it's going to take for that crew to move that pile of aggregate. So now what you can do is you can actually measure the actual production against that planned production, and you can then use the ratios, remember we talked about the production factors, to make equipment management decisions. You know, you can look at how well the trucks are running, what kind of breakdown time you had so that reduce your production. If you had to use overtime to make up for broken equipment, or because traffic was worse than you estimated. You see that what you're doing using the simulation is moving away from concentrating on calculations with one answer to the ability to work at a higher level, to play what-ifs based upon the numbers that you calculated and how you predicted work would happen, and then make adjustments to see what would happen if you did make some type of management change or decision. And that's the beauty in simulation, that you can set up an endless number of alternative ways to approach work and to do work, and you can test them to see how realistic they are and how they might allow you to accomplish a job quicker and cheaper. Now, one caution is that when you're using a simulation model, you always want to validate the model. You have to verify all the assumptions and the inputs to the data, and you have to do a sensitivity analysis. So we mentioned that a minute ago. Sensitivity is simply what factors in your simulation affect the outcome and change the answer in different ways. What has the biggest impact on the answer? What has the littlest impact? And what you really need to do is, when you set up a model, is test it against real data and make sure that that model, when you input data from actual work, gives you an answer that replicates the answer for doing the real work. And if you can do that, you're going to have a fairly accurate model. You're going to be able, again, to spend a lot more of your time making management decisions as opposed to calculating numbers and not being able to test them.